When we talked of harmonic motion, for example, like a spring mass system, something like this, moving up and down. So the y position, we said we can express it as a function of time in terms of a sine function, where a is the amplitude, omega is the angular frequency, t is the time. The angular frequency is, of course, 2 pi over t, so we can write it this way as well. Just as a reminder, when we graph the function, what's shown here in green, the amplitude is the height of a crest or the depth of a trough in the sine function. So we have an amplitude on top of the equilibrium position and an amplitude below the equilibrium position. The period is the distance from crest to crest or trough to trough. It is the length of a full wave. That's the period as well. All of these are the periods. It can be from any point here to an equivalent point on the wave. That's a period. Note here, the x-axis of the graph is time. So it's telling us about how the mass is going up and down as a function of time. But if we talk of waves, this is what we see when we talk of waves. Something like these crests here and troughs that are moving. So what we are seeing here, these crests, they are as a function of position, not time. But then, in terms of position, if you are standing in a particular position, you are going to experience the same thing that we just talked about here in terms of a spring mass system. You are going to experience the water level going up and down according to a sine function. Probably not necessarily a sine function in an ocean like this, but the simplest version of that, the simple harmonic motion, would be a sine function. So what we have in the ocean has to have a sine function not as a function of time, but as a function of position. Something like this. So we see here y as a function of position is something like this. Either 2 pi x over lambda or kx. So k is the equivalent of the angular frequency. We call it the wave number, k. And k is equal to 2 pi over lambda. Lambda is what we call the wavelength, the length of a wave. That's what the wavelength is. Notice here, compare this to the other graph. There you have t. When we have time here, we have t here. Now we go back to this one. When we have position here, we have lambda here, the wavelength. So it's again the distance in this case between crest to crest or trough to trough or any identical point of the wave to the next identical point. That's a wavelength. The amplitude has the same definition, the height of a crest or the depth of a trough. And we can measure the amplitude from the equilibrium position. So to account for what we have position-wise, like we have here, and time-wise, like we have here, what we need is something that accounts for both the time dependence and the position dependence. That's what we get here. So you see our function is actually expressed in terms of, it has two variables, position and time. And our sine, the amplitude is the same, but it is sine of kx minus omega t. So it is accounting for both the position x and the time t. You notice here we have both the wave number k and the angular frequency omega present in that equation. Now, when we have something like this, okay, I'm going to pull in the simulation. So here is the simulation this is the amplitude from here to here or from here to here. In this particular case, it is set at 1. But then let's play it. And that's what you have. So it's a traveling wave. In this particular case, it is traveling towards the right. Now, if I'm standing in a position like this, I'm going to experience zero wave, a trough right now, zero wave, and a crest right now. So if I stand in a position like this, I'm going to experience simple harmonic motion. I'm going to experience the first graph that was expressed in terms of the sine function with just the time. But then when we look at it, when we take a picture of it as a function of position, this is what we see. So that's the equation for a traveling wave.